energy that gets transferred as work or heat. And so our combustion example, our glucose combustion example, or any other chemical reaction, endothermic or exothermic, say if it's exothermic, the heat energy will be released, some energy heat will be released, but if it's endothermic, heat would be going in. But nevertheless, we're going to need some sort of energy exchange with our surroundings, okay? And it can look like work or heat. For a chemical reaction, let's say we have some sort of solid, it undergoes a chemical reaction, and now, because we've released some heat, pressure's going up in this vessel, it's going to push against this piston and expand the volume. And so we will look at this figure again in more detail. But we have one type of work would be expansion of a gas that's released following some chemical reaction against a piston. Energy transferred as work is stored. So if you think of energy transferred as heat, and this will get into our entropy conversation, it's sort of lost to the surroundings. We don't really know how to get it back. That random motion, that randomness is kind of has escaped us, but energy that gets transferred as work, we could put back into our system. And so with this type of expansion, if you were to push the piston back down, you could put energy back into your system. And in this case, my hand pushing on the piston is surroundings. I'm not the part that I said to focus on. Like I said, we will look at this example, this gas expansion inside of a piston cylinder many, many times. But for now, let's switch and define the first law of thermodynamics. Does anybody already know it? It's okay if you don't. Can we destroy matter? No. Can we destroy energy then? No. It's that. Total energy in a system and surroundings. The total energy in the whole universe has to remain constant. That is the first law of thermo. Okay. So another way you'll see it phrased is the law of the conservation of energy. So we're familiar with laws of conservation of mass, laws of conservation of energy. That energy is in some format, okay? It might be heat, it could be kinetic energy, it can be potential energy. We're going to have changes in all these things, but total energy of the whole universe is the same. Okay, and so you can write that mathematically. You can have here this lowercase d is how I'm going to show it on the slides, just because I'm too lazy to put any other Greek symbols in. du is an infinitesimally small change in energy, okay? Whereas like our capital delta is our total change, right? So here we're talking about some microscopic change in energy in the universe would be equal to that infinitesimally small change in the system plus what's changing in the surroundings, and that has to be equal to 0, okay? Because the change in the universe, we can't have a change in the universe. So you can rearrange, when you set that equation to 0, you could just rearrange it as change in the system has to equal to the opposite change in the surroundings. If heat flowed into a system, it flowed out of the surroundings to get into the system, or vice versa. So a change in energy is always matched by a change in energy in the surroundings, an equal and opposite change. Systems energy can change by doing work and or exchanging heat, okay? Giving us a restatement of the first law that looks like this. The change in internal energy, our choices are either some amount of heat transfer plus some amount of work done, okay? And the combination of the heat transferred and the work done gives us the total change in the internal energy. Q, lowercase q, is going to denote heat. On future slides, it might be a capital Q. I will try not to use capital Q, and I will really, really try not to use capital W, because when we get to chapter 7, capital W means multiplicity. And I will try not to confuse people. Notation sucks. But lowercase q is heat. dq is our incremental change in heat. Our W is our work, and dW would be incremental. So we have another way to write this is that delta U in the universe, our total change in the universe, again, has to be 0. Just keeping track of notation. And so then total change in the internal energy of a system has to be heat transferred plus work done.